Okay, welcome back. We have been talking about algebraic abstractions of multiple linear regression, right? So I'll just give you a very quick recap and then move on to estimating the residuals and errors. So this is a little bit of history here, which I don't know why I did not tell you earlier. It's this, is that these multiple linear regression models, I mean, in statistically speaking, this multiple linear regression and linear regression models evolved much before the advanced linear algebra, which means, this establishes my point earlier where I said that just imagine the chaos if you do not have a, linear algebra tools available and you are given multiple observations, multiple data points with multiple feature values, and imagine doing this on a piece of paper. So just imagine the chaos, right? So just imagine the chaos of regression handling without linear algebra. Just imagine this. I mean, this is a situation I can't even imagine. I don't even know what I would have done if I had to deal with a problem like this without having the necessary tools at my disposal. Okay, having said that, so let's revisit the regression model without the matrix notation, which is nothing but this, where we estimate the coefficients beta naught and beta 1, and we have seen the statistical ramifications of these coefficients in the last lecture, where we have discussed at length the importance of measuring these coefficients with a certain level of confidence, 90% or 95% or even better 99%, right? And so these are model parameters, beta naught and beta 1, which you need to efficiently estimate in order to know how good your model is, right? Okay, based on some set of training examples that you are given a priori. Okay, all right. And we also assume that the errors are normally distributed with mean 0 and some standard deviation sigma. Okay, and abstraction of this model, yeah, an abstraction of this model is this. Okay, so where, I mean, this y is nothing but an n by 1 vector, and x beta is also nothing but an n by 1 vector, and epsilon, the errors are residuals, are also nothing but an n by 1 vector. Okay, we have also seen how to estimate these model parameters using the tools of linear algebra, and this is data independent, right? This does not depend on what your data is. So these are data independent estimates, meaning, I mean, it does not really depend on what your levels are, okay, what your y values are. Okay, you should be able to compute this anyway. Okay, of course, in order to know the specific values of beta 1 and beta naught, you need the data, right? But these formulas for estimating the coefficients is independent of y. Okay, all right. So having said that, I would also just briefly recall that the expected value of epsilon is nothing but 0, and the variance of the residuals is nothing but. So this is also known as the mean, right? We know that this is also known as the mean, and mean is called the unbiased estimator. Okay. So having said that, we would also just recall here that the residuals are, which are computed based on the coefficients, is nothing but y minus x beta, and this is important to compute, right? Okay. And we have seen before that the mean square error, which is the measure that we would use in standard regression models, is nothing but overall observations, okay, or the inner product of the residual with itself, and that is why the mean square error throws a scalar or a number at you. Okay, we have seen how to compute these mean square errors, right? And we have seen how to minimize this mean square error using the calculus tools to arrive at the formulations, right? So I am not going to repeat all that, but I just want to let you know that we know this already. An expression, this particular expression, which is nothing but the pseudo inverse, right? Times y. Okay, all right. Now, next, what I want to talk about is that how do we compute the fitted values and residuals? And what is the role of linear algebra in that? Not only that, the fitted values and residuals, how do we interpret this using the projection matrix? All right, I think I have a question here. Some reference for linear regression. Okay, let me type it out. Rajan's notes is one. Also, if you look at this, guys, anyhow, if you miss the class, I mean, all my lectures are uploaded in that in a specific folder, as well as all the handouts that I work out during class, right? So if you go to the whiteboard folder in the Google Classroom, you will see those slides as well as some other references. Okay, but in general, Rajan's notes is a pretty good reference, and also I mean, that should be good enough. Okay, all right, and everything else is in my whiteboard. All right. Okay. So now what happens is we compute the fitted values and the residuals. So we call this so this is also these fitted values and residuals. They are also vectors, right? These are also vectors. So we call this fitted values or residuals as M. We usually in statistics we use the hat notation to denote that we are estimating this, right? Okay, and this is represented as x beta hat, and you know that this is just an n by 1 vector, right? Because x is n by 2 if you recall, and beta is just 2 by 1. So x is n by 2 and beta is 2 by 1, so this is an n by 1. Okay, all right. And we also know the value of beta hat, right? So beta hat is nothing but it comes from that pseudo inverse computation, right? So I can extend this out and I can write this in this form: x transpose x inverse x transpose y. Okay, all right. So this is actually the beta hat. Okay, all right. So having said that, let's now bring everything to a matrix abstraction. Okay. Now, if you look at this m hat is this, there is this chi, right, times y, right? Okay. And since you are representing this in terms of a matrix operation, this is linear, right? And so therefore, we can say this m hat or the fitted values of the residuals is linear in y. Okay. And this is a matrix, right? I mean, in fact, this is a matrix. I mean, I should really be calling this a matrix, right? This is a matrix, and we call this the H matrix or the hat matrix. Okay. So therefore, what happens is that your m hat is nothing but Hy. And so it's like the properties of this matrix. The properties of H actually throw some very useful insights on how this regression models and the corresponding abstraction in linear algebra can be interpreted in a geometrical sense. Okay, all right. So therefore, what I am trying to tell you is that the properties of the fitted values are largely determined by the properties of H. Okay, all right. it's, as I said, if you recall, this is also, I call this as an influence matrix. We call this an influence matrix, and that particular, I will tell you very briefly in a short while why this is called an influence matrix. Okay, and this is not a function of y. Okay, so this is not a function of y. Okay, so this influence matrix is nothing but, you know, x times x transpose x inverse times x transpose, the whole thing. Okay, this whole thing. Okay, now also there are some other interesting properties. So the first property of this influence matrix is the following: is that since this influence matrix is not a function of y, if you do this, if I do this, if I take the partial derivative with respect to a set of observations, you know that if yj is nothing but the set of observations, right? This gives me hij. Meaning what? This hij is nothing but the rate at which the ith fitted value changes as we vary the jth observation. So this is the rate at which the ith fitted value changes with respect to the jth observation. With respect to the jth observation. Okay, all right. And so therefore, the influence that observation has, so this particular thing measures the influence of that observation on the fitted value. Okay, so therefore, influence of that observation. That is the reason it is called an influence matrix. Influence of the observation on that fitted value. Okay. Okay. So now, as I said, H is nothing but x times x transpose x inverse x transpose. There are two other useful properties of H which can be easily verified, and I leave it to you to verify this. Is that the second property is symmetry, which means that H transpose is equal to H. So you take the transpose of H, you will easily be able to figure out that this is nothing but H itself. And the third property is idempotency, which means H square is equal to H. This is also easy to verify. Okay, all right. But I just want to talk about this a little more. So this is idempotent. Okay, I mean, certain matrices are called nilpotent if you raise the matrix to any power, and each and every time you do that, that raised power will return 0 and 0 only. Idempotent is you raise the matrix to some power and it will return the same matrix. So the index of idempotency, it can be 2, it can be 3, it can be 4, it can be k also, right? So H is idempotent. Okay, all right. Now this has a connection with the projection geometry. Okay. And we know that projection geometry, we have already seen the projection geometry has a strong connection with least square optimization. We have seen this before, right? Both from Professor Danda's lecture as well as mine. Okay, so let's discuss this a little bit. All right. Okay, so let me. So I'm going to just copy this H again. So this H is, what did I tell you, is X, X transpose, X inverse, X transpose. So this is what H is, right? Okay. Okay. And I call this a projection matrix. The question is why, right? Okay. Now, I mean, apparently, if you really think about this particular property that H squared equal to H seems to be a little off, right? I mean, what do we do with this? I mean, we have this property, fine, but I mean, what are we going to do with this? I mean, what does it really mean, right? So we know that this Y and this M are n-dimensional vectors, right? So we know that Y is n by 1, and so is M. It's also n by 1. M is just x beta, if you recall, right? So both of these are n by 1 vectors, right? Now think about this. If we project a vector, any vector, onto the line in the direction of the length 1 vector, so I take two vectors u and v, right? I take two vectors, just two vectors u and v, right? And I project the vector u onto the line in the direction of the vector v, and I say that I assume that the vector v has length 1. Okay, then what am I going to get is just v transpose u. Okay, all right. Now we should check the dimensions. Now u and v are both, I mean, by construction, u and v are both n by 1 vectors. Okay, u and v are both n minus n1 to n. So therefore, what is v transpose? V transpose will be 1 by n, correct? So this is n by 1, and this is 1 by n. So vv transpose is just an n by n matrix, right? But then again, u is an n by 1, so this whole thing is n by 1. So this vv transpose is n by n, but this u is n by 1, so this whole thing is an n by 1, right? Okay. So if I group the first two terms together, as I have already done, right? Okay. Since I have assumed that v is a vector of unit length, we know, what do we know about v transpose v? We know that v transpose v is equal to 1, right? And so therefore, vv transpose times vv transpose. If I just take this, right? vv transpose times vv transpose, right, is nothing but vv transpose, right? Because this v transpose v, if I open this up, this v transpose v is nothing but what? This v transpose v is nothing but 1. So this becomes vv transpose. So therefore, what am I saying? I am saying that vv transpose is idempotent. Okay, I'm going to use this. So therefore, the projection operator. So what does it really mean? It means I have already seen that this is the projection operator, right? So what this particular thing means is that the projection operator for the line is idempotent. So the projection operator for the line is idempotent. Right? I mean, the idea is to explain H in the light of a projection matrix, right? So the projection operator for the, you know that matrices are linear operators. So you can, instead of calling this a projection operator, you can also call this a projection matrix, and nothing changes, right? So the idea is this, that once we have projected u onto the line, projecting its image onto the same line does not really change anything. Okay, so we extend that same reasoning over here. So we extend that same reasoning for any linear subspace of the n-dimensional space, right? So for any linear subspace, of the n-dimensional space, right? Okay, there is always some n by 1 matrix. There exists some n by n projection matrix, right? Or we can call it an operator, doesn't matter. There exists always some projection matrix or an operator which projects vectors in arbitrary position down into the subspace. And this projection, mind you, this projection matrix is always idempotent. Okay, so this projection matrix is always idempotent. Okay, now the other way will be more complicated, that any idempotent matrix is the projection matrix for some subspace, but please note that this is also true. Okay, so therefore, if we are able to read off the dimension of the subspace from the properties of the projection matrix, then this whole thing makes really very clear sense. All right, so having now, so basically what is H then? H is a projection matrix, right? So therefore what it does is that it could actually project your vector onto the line. Okay, so now having said that, let's go back to residuals and let's see what these residuals, how these residuals are computed. Okay, so we already know this, that the residuals are nothing but y minus x theta, right? Okay, and using the hat matrix, right, this can be written as y minus hy. We have already seen the equivalence, right? Okay, and so therefore this can be extracted in the following manner. Okay, so hy is nothing but x beta. We have already seen that, right? Okay, because we know that this m hat is, which is x beta, is nothing but hy. So let me write it over here, just recall this. Okay, so this is one thing, right? And so therefore, I mean, this is now my, in the context of the problem that I'm trying to solve, this is now my influence matrix. This I minus H is my influence matrix. So therefore, it's easy to see that this delta EI, delta Yj, which is the rate at which the influence code changes with respect to the particular observation, is nothing but I minus H. You just read off the elements of the matrix and that's it, right? The second one is symmetry, right? Which means I minus H transpose is equal to I minus H. And the third one is idempotence, which is I minus H squared, right? Which is nothing but I minus, you know that I minus H square can be written as I minus H transpose, or rather, sorry, I minus H times I minus H, right? And so this is I minus H, right, plus H square. Okay, right? But what we know about, this is where the property of H comes into play. What do we know about H? We already know that H is idempotent, right? From the previous discussion. So since H is idempotent, these two terms cancel out, right? And we recover I minus H. So this I minus H is also idempotent. And so therefore, having said that, we could use all of this to rewrite my mean square error. Okay, which is 1 by n y transpose. If you recall that expression, 1 by n y transpose I minus H hat I minus H y. And this will simplify to 1 by n y transpose I minus H y from the idempotency of I minus H itself. Okay, So now you are able to write the mean square error in terms of the influence matrix. So mean square error is written in terms of the influence matrix. Okay. All right. So the next job is to find the expectations and covariances. So next is to find the expectation and covariances. Because if you recall, we just assumed that the expectation of the errors would be, 0, but what would be the expectation of the HY from the model, right? Okay. All right. So that is what we need to figure out next. Hello. Yeah.
Sir, could you again explain how the H matrix is idempotent?
The H matrix is how the, okay. So H
Sir,
square,
from this V example.
H matrix is idempotent, that we already knew, right? I mean, I just used that property.
Yeah.
Yeah.
Yeah, it's
Yeah.
a projection of projection.
Correct. Correct. So H matrix is idempotent because the H matrix is nothing but, okay. So okay, let me go back. The H matrix, okay. So H is X times X transpose X inverse X transpose, right? So if you take H square, what are you going to get? It's X times X transpose X inverse X transpose, and then X transpose X inverse X transpose, right?
Yes.
Okay. So what will happen is this X transpose and X will cancel out, and then you have just E X times. So these transpose and inverses could be, interchange, right? You can bring this X transpose inside and then do this some simple algebra, right? Okay, and you will be able to recover that this is going to be X transpose, X inverse, X transpose. Okay, so I said that in the first slide. I leave it to you to figure out why H is an idempotent matrix. It's a simple matrix algebra. You just do this computation inside, and you should be able to recover this H. Okay, so we just use this information. Yeah.
The second and third term are inverse of each other. It's visible right there.
Right. Yeah. The second and third term, yes. That's what I said. You just check this yourself, right? I mean, it's almost trivial, and that's the reason I left it there. Okay. So I just use the fact that H square equal to H here to show that this I minus H matrix, which is the influence matrix in the context of your regression model, is also idempotent. Okay. All right.
Okay.
So okay. So did I save this?
Sir?
Yeah.
Sir, the partial derivative with respect to yi, can you please explain it once? Like, what are we doing there? So, y is the
observation,
vector.
right? Y is the observation, right? Y is the vector of observation. So yj is a particular observation, right? And ixi is a particular fitted value, right? Okay, so when you take the partial derivative, it is like I mean the rate at which you are seeing how a particular fitted value changes with respect to observation. You need to track that in a regression model, right? So in the course of, yeah, so that is exactly what it means, and that's why it's called an influence matrix. Now I think I should have, so treat this when you go back to your folders, right? Treat this as 2, because this should really be 2, and no, I'll just, okay, yeah, fine. Okay, I saved this. Good. Okay. So now we find the expectation first. Okay. So we know that the model is Rather, I'll just write it x beta plus epsilon and all this. I mean, I'm not using the vector notations again, right? You know that this is the error matrix of the residual matrix n by 1 of random variables with mean 0, and you know its variance covariance matrix is just sigma square, right? Okay. So first of all, let's try to figure this out, which is what is this, right? Okay. Now this y, as I said, h is not a function. I mean, function of y. So what I can do is I can pull this y out because these are for prior data. This is not really a variable. So I'll just have this. Okay. And sorry, what am I doing? So this h is not a function of y, so I can just pull this h out, right? And I keep this here. Now, we know that y is x beta plus epsilon, so we just plug it in here. And we also use the fact that expectation is a linear operator, right? Since expectation is a linear operator, I can decompose this into e of x beta, right, plus e of e. Now, what I know is that the errors are normally distributed and therefore the mean is 0. So this term goes away, right? And what I have is that this is nothing but h of x beta, right? Okay. And so therefore we know what h is. H is nothing but x transpose, x inverse, x transpose, and then there is an x and there is a beta, right? Okay. So therefore, I mean, I can simplify this, right? Okay, I can simplify this, and I can say that this is going to be what? Can you tell me what this is? What this will simplify to? Well, this x transpose x inverse x transpose x is what? It's just the identity matrix, right? So this is nothing but x beta. Okay, all right. I mean, which is what it should be. Okay. Now, if I compute the variance, the next one is the variance. If I compute the variance,
Sir, how did we write expectation of x beta is x beta itself?
what? Okay, what else would it be?
So sir, this is expectation over x, or like
This is expectation over x. X beta is m, right? X beta is m. So
yeah,
these are fitted values, right?
yeah,
So if
yeah,
these are fitted values, it will exactly return. So e of m will return m, right? Because you are not really. I mean, this is not an unknown. So therefore, e of
yeah,
something, e of a constant, will return the constant. And so therefore,
yeah.
that's why you just think of this as m. And so expected of m is m, and m is replaced by x beta. Okay.
Okay, yeah.
Okay. Yeah. So the variance of hy is, once again, I mean, I am going to use this expression for y, which is x beta plus epsilon, right? Okay. And what is this going to be? If I have to simplify this out, so this is hx beta plus h beta, right? So what is this going to be? What is this going to be? What do we know about hx beta? Hx beta is nothing but x beta, right? We have already seen that, correct? So what is X beta? X beta is just the fitted values, right? These are just fitted values. So I mean, so once again, because there is not a variable involved here. This is just the fitted value. The variance of that is not going to give you anything, right? So this is simply variance of, sorry, there is an H I missed. I missed an H here. Sorry about that. Okay. Let me not mix it up. Let's just rewrite this. So this is variance of H beta. Now this X beta these are just fitted values, right? So therefore, this is nothing but variance of H beta. Okay. All right. And variance of H beta is going to be what is this going to be? The variance of H beta. What is H? Okay. What is variance of, if I may ask you, what is variance of epsilon? What do you think?
Sigma square.
Sigma square I, right? Not sigma square, because this is a variance matrix, right? So this is sigma square I, right?
Yeah.
Okay.
Yeah.
Yeah. Yeah. So what is this going to be? How can I write this? Simplify this.
And we can substitute the values of, like, substitute the formula for H.
Which is?
X into X transpose, X inverse X transpose.
Mm-hmm. I just want a more compact. I just want a more compact representation of this. Okay. So there is a trick. There is a trick involved, and that's why you already know some properties of H. So please think.
So the training samples, like X is the training sample. So like when we are fitting,
don't go to X. Don't go to X. Use think about the properties of H. I mean, there is a reason why all these linear algebra properties are proved and stated, right?
so we can move H out of the variance term, right?
Yes, but if you do that, before doing that, we should do something else.
Because if H moves out of, it would get squared.
It would get squared, right? Okay.
Yeah.
And H, what is H squared? H squared can be H transpose. I can write it as H transpose, right? Okay.
Yes.
Right. Yes. So if I do that, then what I have is H variance of epsilon, or the error H transpose, right? Okay. And so therefore, this is like sigma square I, right? This is variance of E sigma square I. Now, since sigma squares are scalars, I can just pull this out, and then I have this HI transpose, right? Okay, which once again will turn out to be H square, right? Which once again, this is H square, correct? But we know that H is idempotent, right? So therefore, I use the property of idempotence of H, idempotence of H, and I just get a very compact representation that variance of HY is nothing but sigma square of H. Okay, all right. Similarly, I can, so therefore, I mean, if I want to compute the expected residual vector, right? If I want to compute the expected residual vector, just this, right? This is nothing but I minus h from the previous calculations, I minus h x beta plus e of this, right? Okay, and this will be x beta minus x beta, that will be equal to 0. Okay. Similarly, I'm not going to compute this. If I want to compute the variance of this alone, right? The variance of epsilon alone, I would be able to show that this is nothing but sigma square I minus h. So please verify this yourself, right? So please verify this yourself. It won't be difficult, right? So, but what's the point? The point is the variance of each residual. So if I see here, is that the variance of each residual is not quite sigma squared here now. Okay. No, unless H is a diagonal matrix, which we do not know, right? Unless H is a diagonal matrix. So the variance of each residual and the residuals are also exactly not uncorrelated with each other. You can also see that, right? Okay. So if I use all of these properties, I can finally find the expected mean square error, okay, which is nothing but 1 over n e of I minus h. Okay, all right. And this will turn out to be a simple n minus 2 sigma square by n. Okay, and that is something that we could verify later. Okay. So anyway, so I just wanted to show you that using some linear algebra tools, it's much more easier to find these estimations statistically, the statistical estimations, unless otherwise. I mean, if you try to do some other method, I mean, this will be a nightmare. So these calculations are facilitated by the tools of linear algebra and the properties of linear algebra that we already have seen. Now, in the context of idempotent matrices, I just wanted to just give you a throwback. I don't know whether you recall this result, and this was some time back before test 2, is that let's say my H is an idempotent, right? Let's say my H is idempotent, right? Then the characteristic values of, and if you recall a result that if lambda is an eigenvalue of A, then lambda square will be an eigenvalue of A square. Okay, all right. So for the matrix H square, the corresponding eigenvalue would be just lambda square. Okay, and since H is equal to H square, you can easily equate the two, and you can see that the eigenvalues of an idempotent matrix, strictly idempotent matrix restricted to the index of 2, have eigenvalues either 0 or 1. Okay, all right. So having said that, I think we are done with the discussion on regression. Now I'll just save this and then I'll go back to one other example from Professor Jain's notes. Okay. And somehow it is here, and this is a particularly interesting example. Not right. Yeah. So this is no, not this. Okay. What I wanted to show you is that, not show you, but rather ask you to do is that now in the context of all the regression that we are doing, it will be perfectly sensible to take a look at a Boston or California housing price data set. Boston housing price data set. Let's take a look at this. This is easily available on public domain. Okay, all right, and let me know what you think, because this is a typically multiple linear regression model. Okay, this is a typical multiple linear regression model. Okay, all right, where this X is actually multivariate. In the sense that you have x1 to xn, a bunch of variables. One variable is the square footage area, not square foot. They measure. I think it's something else. Their American measurement is something. Anyway, whatever that is, and then number of bedrooms. Okay, and number of bathrooms, open spaces, a bunch of variables. And some of these, as you might realize when I state those variables, some of these are categorical variables, right? So these categorical variables have to be turned into a sort of dummy continuous variables. Like if there are two categories, you can say one category is +1 and the other one is -1. If there are three, you can say this is +1, 0, and -1, so on and so forth. But there are multiple categories, right? Okay, so it's an interesting experiment just from a statistical point of view, not from a machine learning point of view. I mean, you can write a small Python code, okay, and try to predict the price based on some new data. Or what you can also do is to throw an additional variable, even just a random additional variable into your multiple linear regression model and see whether it throws off the model itself. I mean, whether your prediction confidence intervals are further going down or it's further going up. Okay, and then you can check whether the additional random variable that you have thrown in, whether that additional random variable is strongly correlated with the existing variables or not. Okay, existing predicted variables or not. Okay, all right. So I think I'll end the discussion here, and then in the next week, I think you have test on, as I said. Okay, all right. So Monday would be just a recap. I mean, Monday will be a revision class, and Wednesday is going to be a test. Okay. I am inclined to, for this particular test, I'm inclined to ask some computational problems, which I haven't done in the last two tests. Okay, so that you get a flavor of everything before you get ready for your compre, because your compre will be a mix of conceptual and computational questions. So what you could expect in your compre is that there will be 4 questions, okay, equally weighted, and 3 out of 4 questions will be conceptual and 1 question will be computational, where I will give you some data and you have to do some calculations and show me the result. Okay, so for that computational question in compre, there will be no partial credit. Okay, I'll mention that in the question paper itself. So you have to be really, really careful. All right, and you know that your comprehensive exam is on December 4th, right? So after the test, third test, we will go back to operators in inner product space, which is the last thing that we are supposed to discuss before we wrap up this course. Okay, looking back before the third test, as we are getting to the end of the semester, I would say that we had a good mix of theoretical concepts as well as applied concepts, right? And these applied concepts involved looking at multiple data science problems, such as least square problems, regression problems, singular value decompositions, PCA, and so on and so forth. Okay, all right. So, okay, I think one or a couple of you guys wanted to talk to me about your next semester project. So please stay back, because I'm going to use the same meeting link. Okay, all right, and rest of you can drop off. Compre will be subjective, yes. There will be no MCQ in compre. Okay. Yes, that is why I wrote a message in the class board, right? Like after you finish the exam, you will have 5 minutes to upload, which means that, I mean, if you are finished in 1 hour, you actually have 2 hours to upload, right? But if you are finishing on the dot, then you have just 5 minutes to upload. Okay, Samyuka, it will be chapters 5 and 6. I will write a detailed post, don't worry. Okay, all right, as I have already done. Okay, so please keep a watch for my posts. I think Nupur and Sharvari wanted to talk to me. So you two just, rest of all can just drop off. Okay, you can unmute yourself. Ritik, you can also drop off. I will reply to your email. Okay, Sharvari, quickly, what is the essence? I think I shared that paper with you also, Nupur, right? The same paper, the differential units, differential equation units. Nupur, you can unmute yourself. Nupur, are you there? Hello. I think you are speaking, but you are muted. Sharvari, I can't hear you.
No,
Yeah.
I'm not speaking. I was waiting for you.
Okay, okay. No, can you hear me? You can hear me, right?
Yeah, I can hear you.
Okay. So, so what is the crux of the paper that I asked you to read? Very, very briefly, can you tell me what are we doing? If we have a feed forward, we have a feed forward
generally,
neural. Hang on. We have a feed forward neural network, right? Okay.
yes.
And generally, what we do is we just feed a standard fixed activation function, like we feed a
Exactly.
sigmoid or we feed a ReLU, right? So instead of doing that, what are we doing here?
So instead of doing that, what we're doing is that for each neuron, the activation function would be the solution to a second order parameterized ODE. And depending on the parameters that we learn, so the solutions would be different. So with like the way we train our neural network, along with that, we will also train these additional parameters of that ODE, which would be A, B, C, and C1, C2. C1, C2 are the boundary conditions. So along with those like forward and backward passes, even our parameters would be learnt by the network. And since these parameters, like basically if you vary the parameters of a second order differential equation, you can get different kinds of solutions. And the solutions range from like sinusoidal waves to, you know, exponential functions, and like quite a huge range of solutions. So like that, what happens is your parameters keep changing as the network is learning the stuff throughout training.
Sharvari, let me interrupt you for a moment. So let's say, like, I mean, so see what my idea is the following, that I give a standard generalized solution. I feed a standard generalized solution to in the forward pass. Okay. Now a standard generalized solution could be e to the power ax times cosine of alpha t plus sine of beta t, right? This could be a standard solution to a second order ordinary differential equation. Okay. Now here your alpha, beta, and a are parameters. Okay. Now generally in feed forward neural networks, so this is an arbitrary activation function.
Yes.
We haven't seen this activation function before. We do not know whether this activation function works in practice or not. What we know is that this arbitrary activation function, we are claiming that this arbitrary activation function can also act as an activation. Okay. Now, the point is, my whole point is, and this is the question I'm going to ask you now, and I'll give you 1 week to think about it, is that let's say I feed this activation function into the neurons. Okay. All right. Okay. Now what will happen is that now what I want the neural network is to learn the parameters, in such a way, from the data, in such a way that this particular generalized solution becomes sigmoid from the data. Okay. So if you think really clearly, and if you have to do some of your calculations on your own, and I have done these calculations already, and that is why I'm asking this question, is that under certain strict parameter choices, okay, these a general activation function becomes a specific activation function, like a sigmoid, like a ReLU, or whatever, right? So these parameter values, like for example, I'll just an arbit example I'm giving. Like let's say I set alpha is equal to 0 and beta equal to 1, right? Okay, and I also set a is equal to 0, then I recover cosine of t. Okay, so I'm saying this cosine of t could be an activation function, but this was not what I fed to the neural network in the beginning, right? I fed a generalized solution.
Yes.
So what the network learns, right? What the network learns from a forward pass and backward pass is it learns the values of the parameters so that the gradient is minimized and you are able to classify well, right? Okay, and you have a new activation function. Now sometimes this could become a sigmoid. Okay, right? For example, if you take a sigmoid, just take a sigmoid function, and if you differentiate the sigmoid function twice, you are going to get a differential equation. Okay, just do this yourself to check. Okay, also I don't know if you are familiar with the activation functions which I have written. Are you?
I looked them up. Like I knew sigmoid and ReLU, of course. I looked up I looked up SeLU, and yeah.
No, those are not the ones I have written. Have you looked up mine, the SBAF, the Saha-Bora activation function?
Which one?
SBAF.
No, I haven't looked that up.
I just typed it in. Look it up. Okay. All right.
Okay.
So look it up, and you will see that this particular activation function is a special case of the generalized solution that we have just discussed.
Okay.
Okay. So my whole point is, you have to be able to tell me how the network learns. How the network learns the parameters so that I feed a generalized activation function, and after certain forward passes and backward passes, I actually recover a specific activation which works best for the model. Okay?
So, like, what exactly do you mean by how the network learns?
Like, for example, I told you, right, that beta is equal to 1, alpha is equal to 0, and a is equal to 0. So these parameter values the network has to learn so that the generalized solution becomes a specific cosine solution, right?
Okay.
Correct. So you can do a trial and error, right? You can do a trial and error, but it has to be done heuristically. But I mean, can you do a grid search, right, for the parameters so basically what you are doing is you're testing a bunch of activation functions together, right, and figuring out which one is the best, and then using it to finally do the classification. So if let's say you run your network for 200 epochs, right? Okay, so for first 50 epochs, I mean, you just figure out, you do a grid search and figure out the optimal values of the parameters, okay, so that your generalized solution becomes a specific activation function which works the best for the said given data set.
Okay.
Okay, and you run it for the next 150 epochs. Okay, so let's say after 50 epochs you discover that the best activation is and turns out to be sigmoid in this particular case, right? Then you run it for the next 150 epochs. Okay.
So, sir, like, what am I supposed to do now?
What you are supposed to tell me in a week is that, can you do this? Is there a realistic way of doing this? Okay.
Of implementing this?
No, not, you don't have to implement. Just think about what are the possible heuristics that you can come up with in order to learn these values of the parameters from data.
Okay.
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 All right. Implementation will be later, not now. Okay.
Okay.
All right. All right. Okay. And did you see the Excel sheet that I shared with you?
Yes, I saw.
So you are paired with Om, right?
No, with Mansi you paired me.
Okay. Okay. With Om. So that is, I mean, your project will be something else, but I mean, I want to test your understanding on this paper. Okay. All right. So this is slightly different idea from what the paper says, right? Okay. All right.
Okay.
But you got to understand this paper also. I mean, I can then move you back to this paper also if you want, but that will, don't worry about it. I mean, don't worry too much about the official title, whatever is given in that SOP list, right? So don't worry much. But I mean, you figure out this paper as well, and you have to tell me, as in the context of this present paper, that how these different neurons learn these activations. Okay. And how and when these activations are combined at the final layer so that this network runs well. Okay. So you have two tasks actually, and you can pair up Mansi with, you can talk to Mansi, and you two can together start working on this. Okay.
Okay, sure.
Okay. All right. Thanks. Bye bye.
Thank you, sir.